Okay, well, good morning, everyone, and welcome to X151 to 51A, Introduction to Digital Design and Integrated Circuit. Today, we're going to start our lecture on Verilog. At this point, all of you, if you actually have gone through lab one, should already get a taste of Verilog, what the language is, what it can do, what are the different ways of expressing what you want. Our TAs actually put together a very nice tutorial of some of the basic building blocks of the Verilog language. And so for this lecture, we'll go through some of the high-level components and also talk a little bit more on principle. What are the key components of the Verilog language to make it easier for you folks to navigate the lab. For a big part of the labs throughout both the labs and also the final project, you folks will be working on throughout the semester, Verilog is a language that we'll be using. Before we get to the specifics of language, it's actually always interesting to get reoriented a little bit in thinking about different components in semiconductor technology, right? Semiconductor field. Last time we talked about Intel is actually have been doing a lot of investments in, especially domestically, in setting up their and improving their fab access to both internal and external customers. But very related to that, and I have been having, different generation of this slide just every year, the collaboration between Intel and the TSMC, while they are different fabs, right? Both have their fabrication capabilities. We actually also see interesting collaborations between different components. In particular, for the past few years, Intel actually also have been using TSMC's fab. So we talk about in the semiconductor design, the people who are designing the different hardware, right? NVIDIA, Qualcomm, Apple, they are all designing their different SoCs for different form factors for different products. And once they finish the design, they ship their design to the fabrication facilities. That can be either Intel or TSMC. We'll also talk a little bit like across different technology nodes, how things actually have been shrinking across different components. But if we actually focus on the fabrication side, we mentioned that Intel does both design and fab. And one of their advantages is actually they can coordinate and innovate across the stack to actually tweak their fab for their architecture or tweak their architecture for their fab. But at the same time, there are actually very interesting dynamics in today's semiconductor field when actually my current fab actually doesn't meet my capacity or like requirement. Intel can actually go somewhere else. So this is a good example. Over the past few years, we have seen actually very consistently some designs of Intel has actually been using TSMC's fabrication capacities for some of their designs. So that also exist in the semiconductor space. Related to that, right, we talk about the shrinking number of fabrication facilities across different generation technologies, right? So if you look at like the trend over years of like different technology node, start from something like 180, that's like much older generation of technology, to something more cutting edge, like N5 or N7. And if we look at the number of companies that actually have the capability to provide the fabrication access, we actually see the shrinking number of companies, right? When we get to the leading edge, we talk about how challenging it is to actually innovate and improve the cutting edge technology so that we can still actually get a better generation of transistors every year. It has been actually a very competitive process. For the older generation, you may actually see some of the, very familiar names. Here is TI. Yeah, TI is here. Fujitsu, Toshiba. You actually see a lot of companies. Back then, where actually everyone, like IBM is here. AMB is somewhere, I think here, right? You actually see a lot of companies actually doing having their own fab, have the capabilities actually to fabricate the older generation of technologies. But as we are actually moving to cutting edge, right, where things are shrinking, you actually need to have a lot of investment and having a lot of capital to actually improve generation by generation. We see this shrinking number of companies actually have the ability. We talk about AMD, right? AMD turned into Global Foundry, spin out from AMD, become Global Foundry. And around N16 and N14 for global foundry, right? They actually stop pushing further. Their priority has been shifted to actually refining the existing and mature process instead of actually keep pushing for actually older generation, like newer generation of technology. At this point, if you look at the leading edge technology, right, where it's very dominated by 3 players, and they are actually across different countries, right? Here, Intel domestically, Intel is still pushing forward, talk about a lot of Intel roadmap in actually getting more advanced technology node. TSMC is always there. People call it like the king of logic. They are really good at doing logic fabrication, have been actually advancing generation by generation. Samsung is another very important player, right? They also very interesting dynamics where they're both designing their hardware and actually very similar to Apple, right? They have their phone, they have their own chip, but they also have their own fabrication facilities. And some generations, Apple SoC actually being fabricated with both TSMC and Samsung, right? So there are a lot of this kind of cross collaboration, I guess, cross function across different players in the semiconductor industry. Any other names you folks recognize? Which one? Panasonic? Yes, Panasonic. Yes, that's also a company, right? Because like typically TVs or electronics, but they actually also have actually used to actually do fabrication. Yes, so TI, like remember the first integrated circuit, Jack Kelby was actually at TI, right? So TI was actually the inventor of like the, well, I guess one of the inventor of the integrated circuit, right? Started, he's looking at me. I started at TI, right? So, and, ASMIC, have anyone heard of ASMIC? Junha?
I don't know the details, but I think I
Okay. Any particular dimensions of?
Chinese.
Yeah, so there are, and your name is Justin? Yes, so there are a lot of this kind of, I guess, geopolitical component there. Every country wants to set their own fab, right? And I guess this year, Hot Chips, actually, there's a keynote from Japan talking about like more leading edge fabrication facilities they are having, right? So you see a lot of factors, different countries, different continents, they all want to have their own facilities given how important semiconductor is. So that also be, I guess, multiplied onto this kind of generation by generation, how technology is evolving, but also the growing importance of semiconductor industry. And there are different factors have implications in the design process. So it has been an interesting year. We'll see how many companies will be left as we're actually keep pushing. But I think now those 3 major players has been very stable. I guess everyone is trying to push as hard as possible, and everyone is ready a lot of different types of support from different components. And also there might be actually new players who actually also have the ambition to actually enter this kind of more competitive, very competitive leading edge technology. So very exciting time. Things never stop. I guess we talk about Moore's law, right? It's more a self-fulfilling prophecy. So a lot of people in this industry have been very optimistic and thinking about creative ways actually to push things forward. And as long as there is a strong demand and looking at today's market, right, like AI and a lot of different consumer electronics, data center has been driving a lot of growth for the semiconductor industry. So as long as there's strong demand, right, people will innovate and think about how to deliver interesting products. So with that, I guess we talk about some of the interesting players in the semiconductor industry. With that, just let's get back to the topic of the lecture. Quick recap. We talk about different design metrics. We talk about how we actually guarantee functionality and factor in some of the non-ideal components in the hardware design. Very importantly, it's also to consider cost in the design process. And then the typical when people talk about PPA, right? Power, performance, area, like all of those are very important when we think about different design trade-off. So for this lecture, we're going to focus on hardware description language, and it's in particular Verilog, which will be the language that we'll be using throughout the class. As I mentioned earlier, everyone should have already seen, I guess, a very high level Verilog primer from lab 1, and that's a very detailed actually example with different component. So for this lecture, we'll be mostly focusing on some high level component and what are the different trade-offs. We think about different ways of designing it. And so when we think about hardware description language, right, very importantly, this is a programming language that has been designed to describe what our hardware is. You will see some of the examples that we'll introduce later, but one of the key components is that this language, it acts like programming language, but it's not really writing program. It's actually describe like what's the hardware you want to build, right? It's always this kind of, you need to understand how the different hardware is actually connected together. And then you use this particular language to be more productive in describing your hardware. In particular, we'll mostly spending time on Verilog, which is like one of the most common hardware description language that actually used in industry. Some of you may also have heard VHDL. This is also pretty common. In particular, I guess Europe and Japan, this language is a little bit more popular than Verilog. But a lot of syntax and semantics are very similar to Verilog there. One thing we won't cover, unfortunately, we don't have the bandwidth to cover, but one of the languages that you will actually see a lot in industry, especially through your internship, a lot of our students actually after taking 151, well, it's very easy to get a design and verification job in a lot, like internship as a lot of companies. And one of the, I guess, common languages, especially on the verification you will use is actually system Verilog. Well, if we have time, we'll do maybe a primer of system Verilog, but that's actually very important, especially, and has a lot of very more advanced features from Verilog, especially, and also on the verification front. So those three are more like, I would say, commonly used in industry. There also has been a lot of, I guess, research effort in thinking about the better ways to describe hardware. In particular, I guess MIT, the BlueSpec from MIT, I guess this is probably started a little bit more than 20 years ago at this point. And also the Chisel language actually started here at Berkeley. Both are still hardware description language with the intention of actually generating hardware, but have more advanced programming features to actually make the hardware design process more productive. Those are generally very useful for actually a small team of designers to actually very quickly prototype a large, very fairly complex hardware. In particular, Chisel, really one of the foundations for the RISC-V effort here at Berkeley, right? It's not only, of course, the RISC-V effort has an open source ISA being defined, and that's really what has transformed the industry, right? But to demonstrate this ISA can be actually fabricated and designed in very actually advanced and producing very advanced hardware. One of the underlying component was actually using Chisel as a very productive language to enable students to write a lot of different RISC-V cores that demonstrate the applicability of RISC-V. For folks who have done or will be taking CS152, this will be the language that you will be using for your class. They both can actually generate Verilog. So in particular, like a system Verilog for Chisel. So you can think about like a wrapper on top of system Verilog, and then it's a more productive way to write it. And then, but after that, we'll talk about the hardware design flow. You can actually go through the same hardware design flow, like the same labs, like the labs that you will be going through throughout the semester. So once you get to the Verilog or system Verilog layer, a lot of the tooling side can actually be reused. But it's a better, you can think about, it still describe hardware, but a little bit more like parameterization, better type system to make it a lot easier. But all the tool chains can be used. And there are lots of companies actually using Chisel for their own product design. So it's a very, a lot of users actually using Chisel these days. So in this case, we'll just very briefly talk about some of the histories of Verilog. And in particular, you will actually see some of those components when you actually go through your lab or homework here. It's actually, I guess a lot of things happened in the 80s. One thing you will figure out, and you'll also see a lot of very important, especially when we get to EDA, a lot of important things also happened at Berkeley. There are a lot of things happened in the 80s. At first, like a simulation language, with some of the semantics in Verilog not making sense when you actually take a first look, but it's really used as a modeling, like what Bella mentioned earlier, as a modeling language to actually help people to simulate their hardware. But once you already have this simulation hardware, the next natural steps, why not we just use it to synthesize, to get to the transistors, right? So then it's actually being used for synthesis. So there is a lot of effort here at Berkeley, also in the 80s on the EDA front, that actually many of those efforts actually led to the funding of a lot of EDA companies, in particular Cadence and Synopsys. That's in particular is really thinking about how to do better synthesis from like languages like Verilog to actually to gate level representations. Another thing I find it pretty funny is that one thing with a lot of circuit or semiconductor component, you will see a lot of acronym that starts with V, like VLSI, very large semiconductor integration, silicon integration, scale integration. Oh, thank God, thank you. I already forgot. So LSI, when large is not enough to actually describe how large the circuit is, what people do is just like add a V. It's very large, right? So let's get to another scale, right? I find it interesting, especially when people are actually talking about LLM these days. It's like large language model, right? What is the next after large language model? It will be a little bit up. I guess VLM is for something different, right? Virtualized. But if you add something just, if large is not large enough, you add another V there, it becomes very large, right? But a lot of V in hardware design, especially VLSI, actually start from, not large is not large enough. You need another V here. And similarly, I guess when you have high-speed integrated circuit, high speed is not enough. You get another very here, so it becomes very high speed, and that becomes like a double-nested acronym for a lot of different components, right? So there are a lot of different, I guess, ways of thinking about this kind of high-level languages and into hardware. So Verilog is basically become very popular, especially here in the US. Well, there are a lot more adoptions of VHDL in Europe and Japan for other parts of the world. And it's basically become like the default language that's being supported in a lot of the CAD framework. We talk about after actually when we get to the Verilog, the entire synthesis flow is actually very consistent across different components. One thing you will actually go through in particular for the ASIC lab is really go through the flow lab by lab and see different components, right? So we'll start with RTL design, right? Using this language to describe the different circuit. You'll probably do a FIFO or TCD logic. And then you'll start, lab two is actually about simulation, right? How you simulate your hardware to see whether your hardware behaves as expected, right? After that, you actually want to do the synthesis. We'll get to actually the gate level representation to see actually how your hardware gets synthesized into the particular technology node. And of course, this is a very iterative process. Whenever you have a new representation, you always do more simulation to make sure it actually behaves as expected. And we'll get to the lower level you actually factor in more realistic component. Right after synthesis, if it's also functional, and you will actually go do the place and route your circuit onto the hardware and factor in a lot more realistic delays and area component into your hardware. And if everything actually pass, you will actually get to the fabrication. So that's like the modular flow of the industry that you can always reuse for different components of the design. And you will see a lot of similarities for either ASIC and the FPGA. You will see this kind of more standard flow in ASIC lab, where different labs will go through different steps to get a sense of different tools are actually used in the industry. So with that, we're going through a little bit of different component of Verilog. If you have gone through lab one, a lot of this will actually sound very familiar to you, but we'll focus on some of the high-level takeaways and also some very tricky points you may actually run into when you actually design your hardware. Every Verilog, component or circuit, you'll see it always starts from module definition, right? Module basic describe a component of your circuit, right? What your circuit does, right? Especially when you think of actually from bottom up, right? You start with different basic building blocks, and then you assemble a large component of your circuit. In particular, there have been two very high level, two ways that describe your hardware. One is what people call structural Verilog. Those are basically literally assemble your circuit using some very primitive, like basic blocks, like AND gate, NOR gate, like the very basic logic gates, building blocks that we mentioned last week. And then you can use actually structural Verilog. We'll see an example later to actually connect the different components together. More commonly, what you will actually do is actually doing behavior Verilog, where you actually have more powerful syntax, where you can actually express your intention and your hardware in more productive way. And the behavior log will actually eventually synthesize into the different building blocks, and then so get actually very good circuit in the end. And then one thing very importantly, we talk about layers of abstractions. What you will do a lot, actually have a hierarchical modules, right? You have your basic module building blocks, and you connect some of them together, and that gets to a layer, another layer of modules, and eventually your entire circuit will be this top level that has a lot of different components. So as an example, if you look at this, is something like very commonly you will see in some of the your hardware, right? We mentioned earlier, it's everything starts with module that define what kind of circuit building blocks you have. And once you define your module, you can instantiate later, right? So for example, as an example, when we actually want to do a module called adder cell, it's like a building block for the adder. We always use a module and AND module to say, oh, I'm going to define this particular function called a particular module called adder cell, and here is this part is where I'm going to define what this particular adder cell actually looks like, right? So we want to give a name of this current building block, current component. And then we mentioned earlier, right? Any kind of circuit have like a bunch of input and then produce a bunch of output. We'll talk about combinational and the sequential logic later, but here you also want to declare what are your inputs and outputs, or what are your ports, right? So that's a port list. And here you can actually be more explicit. Here's my input, here is my output. Right? And then you can actually, in your module body, we'll talk about how you actually describe this particular adder cell. But that's basically a very common structure, right? When you actually have this module cell, there are a couple of things you can do. You can actually build things hierarchically to build a bigger adder using the individual cell. We'll talk about that in later. And then you can actually instantiate an adder cell actually using like give it a unique name and using the module you have actually declared. So let's take a look at the example. So we talk about one of the, I guess, more basic ways actually using a structural Verilog. Here we actually define a module. We see this module and my module component, and we're going to do an XOR gate, right? This will be my name, and I have my different inputs and outputs. Explicit mention, I have input A and B. I have one output, and both are single bit. I actually also instantiate a bunch of wires. Wire you can actually just think about is really like wire actually connecting different gates together that I will actually use. I want to have those names at hand to make it easier to describe my hardware. So here I will not go through that, but if you actually go through, I guess, either the truth table and look at the logic, this is basically one way of building the XOR gate using a combination of AND gate, OR gate, and also inverter, right? By connecting all the different gates together, you can actually build an XOR gate, right? So when you actually like describe this XOR gate in structural Verilog, you basically use all the building gates. Like in Verilog, there already is a building definition of NOT and 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 OR gate. So you instantiate a NOT gate, give it a new name, a unique name. This is the inverter A. I'm actually doing inversion for A, and connect the input and output to the gate.
What do we use it as the explorer if we already have the internal signal definition?
Why do we have a instance name here? If we already have it's still handy to have this instance name. Like, for example, when you actually load waves, right? You need to load, which inputs actually go through these waves. And sometimes you may actually have even things actually inside this. So whenever you instantiate, it's always handy to actually give a name so you can actually do that later. But otherwise, like just so confusing there. Yeah, so that's actually how you connect different connect. Always have an instance name. Otherwise, you don't know which instance it is, and you actually need to look at the signal to actually look at what are the inputs and outputs being mapped together. So that's basically a way to actually describe your hardware using structure Verilog and using those built-in gates function here. And when you actually think about this kind of way, right, of course, you can do this, I guess, using different building function, but it's actually very tedious. You actually need to think about how things actually connected and how to actually even think about like an XOR gate, how this actually can be implemented using this basic logic function. A lot of times it's a lot handier if you actually have more powerful operators and you can just use operators directly without actually building things from scratch using those basic gates. So that's where you can actually use this assign statement. Here we're still talking about combinational logic. So there's no state here. We're basically assign input, right? And then it can perform. We'll talk about different operators later, right? Those inputs can perform different operations. And all we do is basically express or describe what's the operation that we want to perform and assign it to the output signal, right? So this is a way to actually explicitly describe a combinational logic and using more clear and simple semantics. So you will hear people call continuous assignment for this kind of behavior. It's basically things happen continuously, right? Whenever anything actually changed on the right-hand side, the left-hand side, the output signal changed immediately, right? So this is basically what we define for combinational logic, right? Combinational logic is basically whenever input changes, output changes, right? So this assign statement, keep in mind, that's basically used to describe combinational logic. Whenever input changes and then output always change. This might be different because this is actually talking about in this particular function, right? It's actually building an AND gate in your hardware, right? This is very different from a function where you actually need to call that function to actually perform that operation. Once your circuit already have this AND gate, whenever your input changes, your output always changes. Make sense here? Okay, great. So with that, there are some like powerful components in Verilog where you can actually start from like basic block and to build actually more complex things. Let's say, for example, we actually have a basic module called 2-input mux, right? Mux2, we have their like specific input and output signals, and we actually build up our mux using a bunch like the structurally using different basic building blocks. We can actually, one thing that is always useful is actually to think about how we actually hierarchically build a more complex system using the basic blocks, right? Once you write down, when you have 2-input muxes, now if I want to do a 4-input mux, I can reuse a 2-input mux and doing selection hierarchically, and that will give me a 4-input mux that I can have 4-input signal and select to like one output signal, right? Once you have this semantics here, you know how things combine, then you can actually start writing or describing this hardware where you already know what it looks like in this language. So one thing that's very important is always know what the circuit you are going to build, right? All the languages are describing the circuit that you have in mind, right? So here, once you know, here is how I'm going to build my muxes hierarchically from 2-input to 4-input. And then it becomes easier to actually instantiate the 3 muxes that we discussed earlier and match the different input and output ports to the corresponding muxes, because we instantiate 3 and each of them will have their own input and output and the selection signal pair. So you want to do the port binding here. And in particular with named port, you can actually be explicit about which signal in my module is being mapped to which new signal I declared in my wire. And here you can actually to build things more hierarchically for Verilog here. And you'll see similar patterns here. This is another example. We talk about the adder example. We'll spend more time on adder later part of the semester. But you can also see we have a module as full adder. We have input, output. Everything here is combinational, right? We have input and output. So here for my adder module, instead of using, I guess, a basic block we mentioned earlier, instantiate like AND and NOT gate together directly, we can use assign statement. We mentioned earlier, assign statement is a way to express combinational logic through continuous assignment here. It's value whenever the right hand's changed, the left hand changed, right? So this is another way, instead of using structure Verilog we saw earlier with muxes, we can actually use some of the more powerful operator directly. And that will be the way of building hardware that you will be doing throughout the semester. You can play with a little bit structure Verilog, but most of the time you will actually using this more powerful semantics to actually use and or directly using the different logic operator. So once we have the basic building block of a full adder, we can actually connect them together into what we call a ripple carry adder. We'll talk about different ways of building adders also towards the end of the semester. But here, actually, you see the carry. I will ignore other signals, but you see the carry is actually going step by step and being propagated through the different full adders as different bit position, right? One thing, again, very importantly, it's always you want to see the semantics of your circuit first, right? What you want to build, and the Verilog language is just a language to describe the circuit. Once you know, this is how I want to connect the 4 full adder basic block together, and then you can write a 4-bit adder. 4-bit adder produce a 5-bit output together and using the full adder basic blocks that you designed earlier, right? So this is another way of doing things hierarchically.
Yeah.
Just the
Care about into the ripple adder.
Say that again.
Did you really care about R, not like the intermediate signals? You just implement the ripple adder.
If I only care about R, oh, you mean just do a 4-bit adder directly for signals? Yeah. Yes. And that will be like what you will do actually when you write hardware here. Here, it's just we're building things like basic by basic, thinking about 1-bit adder. But when you actually do real implementation, it's already like multi-bit ways. You can just do that directly. Mm-hmm. Mm-hmm.
And then if you just define full adder, then anything that you're below that, you know, is an instance.
Say that again, you say.
So A per add 0 to add and all of these instances like that.
Mm-hmm.
And you just define full adder. After that, like every line below that, you know, it's an instance of added.
Yes, so all of those are actually instances of the full adder. Mm-hmm.
They're almost the end.
Yeah, so this is actually, we describe yes, good catch, Connor. So we actually have a semicolon in the end. So everything is actually the same statement. Yes, good catch. Mm-hmm. Let me see whether we actually miss parentheses here. Oh, so all the things in the parentheses are actually port declaration, right? So we actually have all the ports here, but all the different 4 components are basic instances of the full adder. Yes, but the parentheses is actually for the port list here. Mm-hmm. Okay, this is, I guess, a different way, very basic ways of instantiating adders. I guess more complex combinational logic. We mentioned you can actually use this kind of more powerful operator directly instead of using structure Verilog to build things from ground up. And here is like a list of commonly used operators that have actually very big, pretty wide coverage about different components. We'll not go through them one by one, but with those different operators, you can actually do a lot of the combinational circuit design through like this particular assign statement to describe your hardware. You can do a lot of, I guess, bitwise Boolean operation we mentioned earlier. You can actually do, I guess, ternary operation with this. You can also do, in this way, you can do a multi-bit operation doing sign extension. You can also do shifting. So there are a lot of different components you can use to actually describe combinational logic, and all of those will come in pretty useful when you actually think about different components of the design. Mm-hmm.
Last slide, I didn't understand what was happening in the part that says like full adder, and then it has a list of like four parts like add 0, add 1, add 2, add 3, and then semicolon only at the end.
Yeah, so maybe another way you can write it is you do like full adder A0, you can do another full adder A1, full adder A3, and the full adder A2 and A3. So you basically instantiate 4 copies of full adders here. Does that make sense? Because we actually want to have 4 adders. If you look at the circuit here, right? We actually want to instantiate 4 adders here. So all of them actually form from the same basic building block, right? But I actually want to 4, and they need to actually exist. Yes, so if you look at what would be a good example, let's see for this adder, my carry in is 0, right? And my carry out becomes a carry in of the next adder, right? So let's say if you look at the port declaration, the first carry in is 0 here. And it produce a carry out. So here I'm using R0 as a carry out here. And if we look at, oh, this is R, sorry. I'm using C1 as a carry out here. And we look at the carry in next one, those two are being connected because the carry from the previous adder being propagated to the input carry, right? So that's, you can see this connection, and that's why we need to use those wires here. Those are internal wires that exist in my circuit, but not the input and output signal. Okay, good question. So those are, I guess, different ways of writing combinational logic. That's one way of actually using assign statement. That's always one line. You can actually do a lot of cool things with assign statement. There's also other ways to describe combinational logic. What people use, well, I guess, non-contiguous assignment. They're just like more, you can actually use richer semantics to describe different flavor of hardware. And when we talk about this, you will actually see that a lot of this looks like very like a simulation language because it has this kind of event triggering the next event and how things are connected. But this is also being used as a synthesis language. One of the most common blocks that you will see in Verilog is this always block. It's actually a little bit tricky. You will see actually people design system Verilog a little bit differently to separate how you use always block to describe combinational logic and how you use always block to design sequential logic. Verilog is a little bit confusing, but it will make sense. We'll talk about the different ways, but always block can be used to describe both combinational logic and sequential logic. We'll talk a little bit different how they are different from each other. But when we actually design, let's say let's stay in combinational logic, right? We have input, we have output, right? Another way to describe my combinational logic is to actually use what we call always statement. Always statement feel like a simulation language, right? It's like, oh, some event happens and something actually happens as a result. But this can also be used as a way to describe hardware that you have in mind. In particular, when we actually get to combinational logic, you will see this kind of patterns where we have always block, begin and end, very similar like to the square parentheses that we use, right? So it's basically, but very importantly is that after the always block, it has something called sensitivity list, right? Those are basically the triggering event, right? What kind of event trigger you to trigger the hardware to actually enter into the always? It doesn't, like, remember like the assign statement? As long as the right-hand side shifted, my left-hand side value will be reflected immediately, right? So that's why it's called continuous assignment. Here, non-continuous assignment means that my hardware will only shift or only change if something actually happened in my sensitivity list, right? So you can almost think about defining dependencies here. So here in this particular example, I basically include all 3 signals. If any of my input signal changes, I enter my always block. And now you will see the semantics very similar to what we saw earlier, right? So it's basically assigning the right-hand side to the left-hand side, right? So here, let's say if any of my input changes, here I'm actually listing all of the 3 inputs. my output will be updated or propagated accordingly, right? So from the functionality wise, this is actually very similar. You can actually use it to use your assign statement to use a Verilog logic operator to describe the same circuit, just using one line instead of using this basic block, always block here. It may look actually very similar. For those two parts, those are actually equivalent, right? If any of the input change, actually my output will also be changed. What's nice about always block is that once you get to this kind of more, you can actually use more semantics or more operators to describe your hardware that actually doesn't exist if you actually stay outside always block. What do I mean by that? What are some of the examples here? So here with always block, there are some just part of the language. You can actually use a little bit more semantics here. In particular here, we talked about the muxes earlier, right? So like for muxes, we talked about how we actually design that. Once you have actually always block, you can actually use some of the newer, like different keywords that can be actually useful to describe some of the components. In particular, here you can actually use case statement, especially very similar to a switch statement. Actually, you will use in other programming language. You can actually just say here, I have different conditions, right? I can actually do, based on my select signal, whether it's 0, 0 or 0, 1 or 1, 0, I will actually pick different output, right? This is still a mux, right? 4 input mux. Based on the different selection signal, I will pick different input that's being propagated to my output, right? That still makes sense. This is still a mux. But here, instead of using, I guess, all the different basic block gates that we actually constructed earlier, we can just use, I guess, case statement. Very similar to a switch statement, you can actually do the design. It's just a lot easier to write your hardware. That's all, some of the benefit of actually using this. In particular, maybe a little bit more on the case statement, you may actually run into in some of your interviews and also in some of your actual designs. In addition to a case statement, right, you could also describe the same circuit using just nested if and else, right? So alternatively, what you can do actually, again, the same 4 input mux. Right, you have your always block. Any of the input, all of the input signals are part of your sensitivity list. Right. Alternatively, inside your always block, you can also do if and else. Right. If select is this, I do this. If select is that, I do that. Right. This could also be another way to describe your hardware. This is still will generate a 4 input mux here. But one thing in particular for this particular design, when you have nested if else, is that for the previous version, when we actually have a case statement, all of the input selection is the same priority. Basically, when we look at the signal, we actually will pick one of the inputs after the same delay because all of them are treated the same. But you look at the timing or the execution of this particular design, you will actually do things, you will actually select the different signals by the sequence of the if and else statement. What do I mean by that? I'll get to you in a minute. You will actually first check whether my select signal is 0. If it's true, I will immediately output the input 0, right? But if it's not true, I get here. And then I will actually, depends on whether it is 1 or not, I'll do my second output. And then I do my third condition, and then do a third output, right? So here it's more like a cascaded logic because I'm having this if-else statement, which actually encode a flavor of priority in the design. Yes, Justin has something earlier?
Yeah, thank you. Except by just making sure it blocks, like, not else, but just if they're.
But you're going through all the if blocks simultaneously?
Yeah, right.
You say if input is 0.
Yeah.
And
like, wouldn't they be like simultaneous?
Oh, you're saying what if you don't do else here? You just have 4 parallel ifs. You have if select is 0, output is 0, get to input 0. And then you have in parallel, you have another if statement and say if select is 1. That's a good question. Let me give that a try. Actually, I don't know what's the hardware it will generate.
Pretty sure it's the same, but everything should be around about the same way.
I think what we'll do is just have 4 parallel comparators there. It's still the same select, and then you will just do 4 parallel comparators.
Select is propagate.
And propagate, and then you probably need to do some output select in parallel. Because you're keep reassigning the value to the same output signal here, right? So you may actually, I need to change this. I need to double check, but the idea, you may actually need to assign it to actually different output signals and then do a mux in the end to select which output you want to go.
Sure, that makes sense, yeah.
Right, so because you cannot assign the same values to, I guess, assign to the same output. Yes, that's a good question.
So in the last week, you like positive, so without that positive evidence, when does it trigger the anomaly?
That's a good question. We'll get to positive edge. So in the lab, the reason you're doing positive edge because we're actually designing a sequential logic. So you already have, we'll see that in a minute, but whenever you have sequential logic, you need a register there. But here, everything is still combinational. So there's no clock in the signal. You look at what we have, there's no clock. We're still talking about combinational logic here, right? So that's why we haven't seen the clock pass edge there. When you see the pass edge, that's basically when you start doing actually sequential logic. That's a good question. Any other questions? Oh, here.
Is there ever like actual advantage, say like you had if else, but like you frequently instead at first it would be like taking like 90% of the time or something like that? Like is there any like actual hardware advantage?
Yeah, like for example, if you really want to have a like high priority pass that you really cares, you want to make that faster, you always want to pick that first. We'll talk a little bit later. For example, when you have a reset signal, you always want to prioritize reset signal. That has the highest priority before checking other signals there. Okay, so here is, I guess so far as we mentioned, we have been talking about sequential logic, combinational logic. Another actually, I guess term you actually have been playing with is this generate statement that actually also very useful to actually have more parameterized design. So here, this is, I guess the adder example we mentioned earlier. We have actually this kind of repeated declaration here. But once you actually, another way is pretty useful when you have actually a more generalized design that can be actually useful. Instead of having 4 copies that we have seen earlier, you can actually make it easier to describe, express your design, right? So here, what you will see is that instead what we did, we have like 4 rows and each row is actually explicit, like instantiate another adder. Full adder, you can actually use this generate statement. And with this generate statement, you can actually introduce a loop here. You can actually use a loop to actually describe multiple copies of the instance here. So in this case, you have actually more parameterized. You can use this genvar I here, index here, and you can actually use a different index to actually describe the loop, like the different bits actually being used. And here for this particular, I guess, for adder instances, we can actually instantiate 4 adders here. So that's another way of actually doing things more explicitly. So that's been very useful in some of the design part as well. Justin?
Oh, sorry.
So, okay, well, any questions here?
Do we always have to like define big and dot and bit, or is it just saying the bigs and define
So bit is useful when you actually load your signals. When you load the instance, you can actually see bit as like, oh, here is this bit, like this is my instance. Otherwise, it will give you some like random, like gen something names. Then so it will actually assign a name by default, but it's easier if you have a unique name and then you can load it in your waves and then to see what that is.
It says that generate words, synthesis time operation. I was wondering what isn't all of HDL like this is time operation.
And synthesize time is actually when you actually synthesize into the gate here. So here, This starts from a simulation language, right? We talk about Verilog, you can do actually simulation, but when you actually generate what the hardware being generated, that's part of the synthesis process, and that will generate 4 copies of different hardware there.
The structural syntax is the are making the gates.
You're explicitly, yes. And here is like, you are not making the gates in HDL yet, but when you actually synthesize it, it will actually have multiple copies of the gates. Components can be viewed as like, actually things are actually generated, yes, in synthesize time. So yeah, so this can be actually very useful. You can also see parameterization here to have actually multi-bit components here. So just a quick recap, when we actually talk about Verilog, so far we have been looking at combinational logic. Combinational logic, there generally have very high level 2 ways of defining combinational logic. You can use assign statement, just very handy to actually directly assign components. And one thing you will notice that whenever you use assign statement, you always assign value to a wire here, right? So you assign value to a wire to actually, and to Justin's component question earlier, we cannot assign to the same wire with different assignment there. So we need to have actually instantiate different wires there. But it's always a wire here. But when you actually use always block to describe a combinational logic, we talk about you can actually explicit list all the inputs there. That's one way of doing that. I always recommend you just to add a star here. It's just very handy. It's basically any of the inputs, right? So that you don't actually forget any particular input in your assignment that will lead to incorrect circuit, right? Always use a star here. But one thing we forgot to mention earlier, whenever you use always statement, the output that being assigned to should always be a register, which is actually very important. And I forgot to mention that when we talk about always block. So here, one thing in particular is when you do always block here, you always announce it is a register, but it's just a Verilog. It is, you are not actually instantiate a register in your hardware. It is not a register, but you can only assign to register in the hardware in the always block. So it's not, will not be synthesized into a register, but just a semantics. It's still a combinational logic. There's no register, but it has to be instantiated as a reg in Verilog so that it can be assigned to the always block. So back to where we were here. So 2 ways of describing combinational logic, either using assign statement, then it's being assigned A is a wire. And then do the always block, just you always use always star. And then here you need to declare A as a reg beforehand. But so far there's no register being synthesized yet. Sure, yeah.
Always, the one with the
always
always and yes. I think that when the synthesizer synthesis circuit, the item, the output you writing always will give you a latch, but the component design in there are designed just logic blocks, logic gates.
It will. Why do you think it will give you a latch here?
Because it's probably always block.
So always block can be, we'll talk about, I think you're thinking about latch synthesis. There is a scenario when actually things done incorrectly, hardware, it will actually generate a latch. But in majority of the case, whenever there's a latch, it's never intended. That means something is wrong in your hardware. And in this particular case, it will not generate a latch here. Well, we'll have an example here. But whenever you see a latch being synthesized out of an always block, we'll talk about flip-flops and latches. Typically means something is wrong in your hardware. It's not intended. So whenever you see latches, something is wrong in the hardware here. So maybe related to that, I think things have been a little bit abstract talking about the semantics. Let's take a look at some of the examples. So here we have 3 combinational circuits using different ways of designing different components. We have 3 examples. One is I guess 3 input adder with A and B and the C to output. B is very simple, just input and output. And C, we actually play with case statement, right? Maybe spend a little bit more time on those three examples. Are those combinational circuits correct? Will they actually generate intended hardware that you have in mind for the different functionalities? We'll wait for a couple minutes before we start. Unless there's clarification questions. Mhm.
So previously, the circuits would always mark as not to is there like and the right equation is just implicit this is still up there. So why do they still follow this always or
how about this? Let's go through those examples and we'll get to the questions. Otherwise, we're interleaving a lot of different things here. Are you also asking? Okay.
The example generate, and then you have begin, equivalency. What is the bit?
Right. So that's what we discussed earlier. It's just give you a unique name. So when you load the wave, you can actually, it's basically a name like being attached to the. Oh, you put there. That's what you write. You give a name. The name is bit, or you can have your whatever name you have. It's bit, and then we'll attach something behind it to differentiate this. But it will start with bit. Yeah. Otherwise, it has some default chain, blah, blah, blah. So it will give a name by default, but it's better to have a more unique name. Okay, well, let's go through those three examples and we'll get back to the always block questions. First, let's look at the first example. So we want to do a 3-input adder, and here we use always block to describe this combinational circuit. Is this one correct? Any guesses? Any thoughts?
it's not perfect because
Exactly. So this sensitivity list is very important here, right? So here we're missing one of the input for the sensitivity list, right? So that's one thing we'll actually see a lot. When you actually use always block for combination logic, you may actually miss some of the like a triggering event. So that's why we typically recommend just always use always start if you actually what you want to design is a combination logic so that you don't miss any of the input.
So this probably would give you a latch.
Yes, if you actually run into this because you actually miss when C actually changes, doesn't do that. So next we have example B. Here we have input and output and we mix things together. Is this circuit correct? Bella?
But it's
Right, exactly. It's a little bit odd, right? So we are writing this, like what we are writing this, we have output. And if you think about the circuit that we have, right? So we have I guess we have an AND gate here, but this is my input, this is my output, and I'm actually connecting my output to my input, right? What does this circuit do? It always be false. Why? Well, it's output, like let's say, well, input can be anything, right? But output just oscillating because output being connected to the input here, right? So output is basically not defined here. It's using the value that is actually not defined and propagates through the gate. So this is where you see what people call the combinational loop, right? So the whole circuit doesn't stabilize, right? Because your output being refeed into the input and then it's actually have a loop. And this is a scenario you should actually avoid. Never actually implement the hardware with a combinational loop because it actually doesn't stabilize. You don't know what the function is, right? It just keep looping there. So this is the hardware, again, another pattern and this is less about the language, but it's really like what's your intention of the hardware, right? Don't actually have what people call combinational loop in your hardware because it's not clear what the hardware actually wants to do. Okay, we have a final example, the case statement we discussed earlier. Is this one correct?
It doesn't have a case, but it's 1-1.
Yeah, so in case though have two, I guess, 2-bit selection signal, right? But it actually miss a case when actually your select is 1, 1, right? So here, if we actually miss that, what does this circuit actually generate? What does this circuit? How do hardware or the synthesis tool interpret this circuit? So the tool will actually, well, yeah, whether this will be a mux with something, the tool will interpret that you actually want to have this behavior where for this particular 1-1 scenario, it is undefined. So I should actually maintain the values I had before, right? Because there's actually not being changed when it actually has that input. So this is what I think your name is. Yeah. Azure mentioned earlier, this will also generate a latch for you, right? Because now I don't know, there is a condition, you never tell me what I should do, and I will actually maintain the old value here. So here I'm actually generating a storage component to store it. And this typically, again, whenever you see latch being synthesized out of your combinational logic, it typically means something's wrong in your circuit. That's actually not intentional. So this will also generate a latch, but it's actually not intentional here. Mm-hmm.
That will be, is it possible to do that with let's say it's XOR gate and then it becomes like a flip-flopping kind of thing? Like, there's a delay with the gate, right?
There's, if you add an XOR gate there.
It starts with 1, 0, and then it becomes 1, and it becomes 1, 1, and it becomes 0, and it goes in.
But there's delay, but there's still a loop there, like the output still feeding.
It's still the same.
Oh, you're saying this become an XOR gate?
And then later, maybe there's like a use of delay.
It delays, but it still doesn't have this clocked. There's still no clock, right? When you think about flip-flops, right? It's not a. So it has certain delays being propagated into the circuit.
Yes, because I know in analog, like they do something similar.
Mm-hmm.
A delay.
I guess you can think of it as you can have a buffer, but it's like more cascaded buffer, right? You can actually have cascaded. So that's another very common way actually just have cascaded buffers to add delay component. This, at least in digital circuit, this is, unless you intentionally want to have, right? For delays, it's more common just like having cascaded buffers there. I guess I don't recall a particular scenario.
That would be super. It's just one gate.
But like, what is the output of that gate?
It's just time dependent. So it's either 1 or 0, and it's dependent on the delay.
It depends. Oh, so you want to use this gate?
The delay is 1 nanosecond. The delay would be like, it will be 1 and then 0, and then the delay will be 1 nanosecond.
For the so you want to measure the output of the delay for the output signal here?
Yes, that would be the delay of the game equals to the delay.
The delay. So you want to see how the output signal actually transition from 0 to 1. So this output is used somewhere else.
Yeah, somewhere if you need like a flip-flop.
I need to look in. I guess I don't know. Like Ben, do you have an example of that?
You could do it, but it's a really bad idea. Verilog is a very flexible language, right? We'll talk later, there are constructs that are not synthesizable, that are only used for simulation, and you can write those down. And then there's an awful lot of stuff that you can write down, and the tool will do its best to synthesize it, but you really ought not to. And so what we're showing you here is kind of like stay on the path, which is like a few very specifically defined things that if you do this, then you'll get good results. And if you stray off the path, it might still maybe work, but it's probably not doing what you want. It's probably not doing good results.
It's like this language being interpreted by the tool, right? The tool will generate something. I guess you have your best intention to use a language to describe it, but the tool may or may not to do what you want, right? So yeah, as Ben said, here are some best practices that always work, and that works and that has a more predictable outcome. But for other things, weirder, you probably either just go to the transistor level to actually manipulate it directly, or you need to be very careful what the tool actually will produce. That's an interesting thought. Okay, so those are the 3 examples, but I guess before that, there was a question about always block. Can you say that question again?
Yeah, just like if reg is the only distinction factor between always and just using raw convolutional logic. And if reg is just a liar, then one is still logic.
So we'll talk about how always block used for sequential logic next. So it's not only just for this. Like, why do we want to use always for combinational logic? Oh yeah, so like for example, some of the case statement with like those operators only exist in always statement. It doesn't exist outside the always statement. So those things are what actually being useful when you actually think about more complex things. Yeah. Okay, good. Okay, so a lot of different components here. Just a very, I guess, announcement. We have homework out last week and due this week. Very simple, very basic. There's some high-level components. Discussion started last week, and also lab 2 also start this week. I guess for Monday students, you folks have already started lab 2. And office hours. So because again, we got some very good feedback last time, so we're changing office hours. Ben will actually move his office hour to 2 to 3 today. I guess Tuesday.
Yes, I'll be there today.
And you will start today. So I originally have my office hour, I guess, right after this. I will still keep it today because I already have something booked for Thursday. But starting next week, it will be Thursday. But I still have my office hour right now, today, right after the lecture. Okay, great. I guess we have gone through enough about the combinational logic. Next, we're going to get to the sequential logic, but we're already about the time. We'll do the sequential logic next time so that we can actually have a clear separation. Well, good seeing all of you. I guess we'll see you next Thursday. Okay, let me stop.